Hi, I'm Mike Hoffman,
And I'm Daniel Bogdanoff.
and we're here today with Rick Eads, who's going to tell us all about why PCI Express will take over your life.
So, Rick, tell us a little bit about your history with PCI Express, because I know around here we're going to start calling you PCI-Eads.
Oh boy, PCI-Eads. That's a new one for me. Okay, yeah, sure. So PCI Express started in the early 2000s, I guess 2002, and I got asked to work on some stuff for scopes, and then I got involved with the PCI-SIG. And so I've been doing PCI Express stuff since their initial PCI Express release, which was running at 2.5 gig. Since then, I've done lots of work in the PCIe space. We've gone from Gen 1 to Gen 2 to Gen 3. I served for 7 years on the PCI-SIG Board of Directors, so I kind of understand a little bit more how the organization works itself. And I participate mostly on the side of the physical layer definition. So, signal integrity elements, transmitters, receivers, and that portion of the specification. A big part of the spec is in protocol. So I'm not as deep into the protocol side, but definitely on the physical layer side from a transmitter and receiver standpoint.
Okay, great. Could you give us a brief overview of what PCIe is? My whole experience with it pretty much is just plugging in a video card into my computer.
Yeah. So, if you think back, there's always been a need to have some type of interface between a personal computer and the outside world. Originally, there was a thing called the ISA bus, which was the main mechanism you had to plug in video cards and things like that. And that transitioned to a very successful standard called PCI, which is the Peripheral Component Interface definition. And that worked really, really well, but it started to run into speed bumps. People wanted it to go faster. And you think about what's happened in the last 15 years in gaming, for example. There's been a real drive and a real market built around overclocking and faster performance. And so that was a bottleneck, and they really wanted to improve that. So PCI Express was a revolutionary change in the interconnect for a personal computer. The PCI bus and the ISA bus before it were parallel buses. That meant that you took 8 bits and you laid it out parallelly, and you latch in 8 bits at a time or 16 bits at a time, depending on the width of the interface. So what PCI Express is essentially flipping that into a direct serial domain and driving it at a much higher speed, where you were going from hundreds of megahertz with PCI. PCI Express goes in the gigahertz range, right? The first instance of PCI Express was 2.5 gigabits per second. So that was a lot faster. Now, another thing about PCI Express is it's scalable. So you could have one lane, very simply, running at 2.5 gig. So you have basically one differential pair that goes out that transmit, one that comes back and receive. But if you need more bandwidth than that would give you, then you can scale it up. You can scale it to 2 lanes, transmit, 2 lanes receive, 4. You could do 8. And then the most practical implementation for the widest is 16. So you can throw out 16 lanes of PCI Express transmit and 16 receive. So that gives you a lot of scalability in terms of bandwidth and performance.
Big time.
Yeah.
You said most practical. Can you go higher than 16 lanes on PCIe?
Yeah, I'm pretty sure the standard will go up to 32 lanes.
Oh, okay.
And so the most common you see are by 1, by 4, by 8, by 16. By 2 was really fairly uncommon until some of the more recent SSD devices. But
okay.
That's actually a good lead into what I was going to ask next. So I know PCI Express is very popular today for graphics cards and for network cards and things like that. But it sounds like it's making a transition into other parts of a personal computer or a server. It's like storage, as you just mentioned. Can you speak to that?
Yeah, that's correct. After the 3rd generation of PCI Express was introduced, we call it Gen 3. Colloquially, officially, it's PCIe 3.0. After that was introduced, there was a transition in the market that happened where solid-state storage drives started to become more and more popular. And if you think about just how much bandwidth is sucked up in video, right now on the internet, a lot of that has to get served by a server system. And SSD drives have a distinct advantage over magnetic media in that they're a lot faster. So they needed a standard that was faster than what they could get with like a SATA interface and the like.
Interesting.
And so an organization called the Non-Volatile Memory Express organization came to us as a board of directors and said, "Can we use your standard for, your physical standard for our interface?" And we're going to create a new standard called NVMe that's PCIe-like, but only really uses the PCIe physical layer, and then is really targeted toward SSD storage on the protocol side. And what's interesting about it is there's a lot of things in SATA and SAS that have to do with sectoring and interleaving data and how you put data and write it down onto a spinning disk of rust.
Sure.
On a
Rust.
iron oxide or whatever. Yeah.
Sure.
And so when you take the rust out of the equation and you make it sand, then that's a whole different kind of a thing. Because it turns out sand is a lot better than rust. It actually is quite a bit faster. So because of the speed advantage that you get with SSD drives, they decided to go immediately to PCI Express because they could get there fast. It was a well-baked standard. It had good interoperability, and that led to the adoption of PCIe into storage.
Interesting.
So is that something that we're seeing in consumer-grade equipment, or is it mostly just server kind of style applications at this point?
You do see it in consumer-grade equipment. Like if you look in a laptop, for example, or most any motherboard that you might buy if you're building your own system, you'll see a small connector in there called M.2. And M.2, in the context of a laptop or otherwise, is designed to take an SSD drive to plug in. And typically those will run NVMe or a thing called SATA Express.
Yeah, I think my laptop actually has an NVMe drive in it.
Yeah.
And my hard drive is tiny. It's like a
micro SATA is
SD
still
or
there,
SD,
but you'll see things like SATA Express, which is another kind of flavor of this storage idea, right?
Interesting.
So if you have SSD drive, it can run SATA Express, it can run NVMe. NVMe is really more targeted towards the server space, certainly, but the speed and just the reliability of the PCI Express component of it is really now becoming the standard interface on the storage side.
Okay.
As opposed to just the I/O, just the interface to the networking card, or say to the graphics interface.
Is PCIe used almost exclusively for some sort of peripheral to another like host device, or is it used on a single board? Are different parts of the board talking to each other? Does that make sense?
Yeah. The short answer is both.
Okay.
It is designed to be an interoperable standard. I mean, the whole purpose of having a standard is so you can design, say you want to design a motherboard. We call that a root complex or a host, right? So you design the host, right? But you want to make some money because you have this really cool idea to come up with a very high speed Gen 4 capable RS-232 interface.
Hey, don't tell everybody my idea, okay? That's my nest egg.
Right, and you don't want to tell anybody. So what you can do is, being a member of the PCI-SIG, you get access to the standard. You can design that independent of even talking to him. And if you design it to the standard, then when you plug it into his motherboard, it's going to interoperate. So both of you can operate independently and do your development independently.
Thank goodness.
And you have a greater likelihood that what you come up with is going to be interoperable. So that's the whole purpose of having a standard. I mean, There are a lot of people that create high-speed serial interfaces, and that's not necessarily PCI Express. You can run LVDS between two points. Come up with any type of protocol you want. If you own both sides of the root or the host complex side and the endpoint side, do whatever you want. It doesn't really matter, right?
Right.
But the whole point of having a standard is that you can build something independent of another person, or you could build one device, and for everybody out there that's building a motherboard, you would be able to plug your device into there, so that expands.
They all play nice.
Yeah, and then your motherboard would become more utilitarian to a wider audience because it would be more adaptable and extendable and expandable because of all of the things that you could plug into it. Right?
That makes sense.
Yeah, so it goes both ways. So that's what PCI Express was built around.
Okay. And then if I understand it right, your specialty, and your expertise that you brought to the standards body is that Mike needs to make sure his peripheral works, and I need to make sure my root complex works. But we don't want to check it with each other's boards because it's all, company secret type stuff. So you have to test it somehow.
Yeah, I mean, eventually you'll want to, do some interoperability testing. But, if he's early on in the project, and you find this a lot in the industry, they don't necessarily want to share a whole lot with what they're working on, right? Until they're pretty much done and they know where they're going. And then they'll, start to reveal that, yeah, we have this, we're going to do some interoperability testing. But a lot of times they'll buy things, bring them in, test them in-house so they don't have to reveal stuff. But in the end, there is part of what the PCI-SIG does is we hold industry-wide interoperability workshop events.
Oh, okay.
And these are, mostly NDA activities. You're not supposed to talk about what goes on in the workshops outside of the workshop.
Sounds a little sketchy.
But somebody can bring, sounds a little sketchy.
Yeah.
It's kind of like Fight Club. Yeah. First rule of an interoperability workshop is we don't talk about what goes on in an interoperability workshop. But it gives someone the opportunity to bring their proprietary or new prototype there to test it early. And literally, we have had cases where people have brought in products, large root complex devices or otherwise, that are covered in big, giant, hefty trash bags. And all you'll see is a port, and they'll say, okay, you plug in your test device right there. It says, well, what is it? Well, we can't say. It says, you tell us what you need, you plug in it, this is what we're giving to you. And the rest of it's in a big box. You can't even tell how big it is. You don't necessarily know. But you test the device there, and the door is closed. No,
Interesting.
They don't reveal what it is. But it gives folks an opportunity to test, and literally over the years, since the early 2000s, we've tested, over 1,000 devices that way, easily. And it gives companies a chance to start to engage with the industry and in a very controlled way, determine if they have any issues when it comes to interoperability.
Well, to change the subject a little bit, I had a curious question for you that I was thinking about earlier today. A large portion of our audience out here uses PCI Express every single day. Sometimes they carry it in the pocket, definitely in their backpack, at their desk, and they maybe don't know it. Thunderbolt, which I believe, if I'm correct me if I'm wrong, is kind of a combination of PCI Express and DisplayPort into one standard, which of course we use to charge iPhones and things like that. What kind of dynamic was there when they wanted to go forth and create this new standard? How did they work with you and the rest of the SIG to do that? They need your permission, or is it an open source standard, or do they pay you royalties?
Yeah, well, we do have groups that come in and want to ask us for access to our specification. In the case of Thunderbolt, they may use some theories of operation that we have. They do not leverage the written documents that we've created, what we call collateral that describes the operation of PCI Express. PCI Express, for example, is really a build off of some of the physical layer characteristics of InfiniBand. So how much work did we do to go to the InfiniBand Trade Association to talk to them about getting permission to do PCI Express? We didn't.
Right.
Because when you build a physical layer, a PHY, if you think of yourself as an IC designer, do you want to build a Thunderbolt PHY, a USB PHY, a PCI Express PHY, a SATA Express PHY, a SAS PHY? Do you want to build all those different PHYs?
No. Definitely not.
Or Ethernet PHY, 10 base T, 1,000 base T, whatever. 10KR, I think that's the one that comes to mind. No, you want to build something that's more universal, right? Something you could adapt to all of the different standard characteristics and try to create a single PHY that it acts as a superset. So what you find is that that's the general trend that industry tries to do. They try to build PHYs if they can, so they limit the number that they actually have on chip so that they can support all of the different standards that their chip might be called upon to support. For PCI Express, you do find it on some mobile devices. PCI Express, turns out, has some very low power states that allow it to be very adaptable to offer very high speed when it's needed, but consume very little power when it's in a standby state. And so there are some mobile devices that do use PCI Express internally as a mechanism to drive data to and from the display. Or from other chips on there. So you asked about, what about, there cases where PCI Express is used chip to chip? Absolutely. There was a couple of automotive vendors, for example, and one manifestation was they used to put the rear view camera display in the rear view mirror. I don't know if you've ever seen any automobiles like that. Well, one of the vendors that provided that used PCI Express technology to go from the camera up into the rear view window display.
Okay. How long, and it probably depends on the spec, but as you say that, I'm thinking that's a kind of a long way from a review camera to a review mirror. How long can you transmit data effectively over?
Well, there is a cabled version of the specification. Actually, there's two cabled implementations that are supported for the specification. One is designed to be more short. One is intended to be longer. And with the longer one, you can actually use an active cable if you need to handle the signal integrity concerns that you might have with the loss.
That makes sense.
And then there's some proprietary implementations where you would drive PCI Express to some type of repeater, and then it would be proprietary from the repeater to the receiver, and then it would turn back into PCI Express on the other end. So there's a lot of different ways that people accomplish that. They didn't necessarily maintain a full PCI Express standard all the way through the cable.
That makes sense.
What's the longest PCI Express link physically you've ever seen implemented?
For me, it's probably been about 20 inches.
Oh, okay. It's not like
watch out,
some sort of array across a building or something.
I mean, these are more niche applications.
Okay.
Of the billions and billions of ports of PCI Express that are out there, most of them are in some type of motherboard or backplane.
That makes sense. Okay.
Yeah, it can be used in cabled and even within Keysight, we've used PCI Express in a cabled application in some of our instruments. But it's by far from the most common mechanism for implementation.
Well, I think we're knocking to about 10 minutes left. Maybe we should spend some time talking about Gen 4.
Sure, we can talk about Gen 4.
So that's been in the works now for a couple of years, and it's looking for finalization in 2017. Is that correct?
Yeah, I think we've at the end of 2016 we fixed the feature set for PCI Express Gen 4. So there's not going to be any new features that haven't been already talked about, unless something comes up.
Like you set it in stone. You didn't fix it broken. I was like, what is broken? Well,
it's in wet concrete right now.
Okay, it's a little slushy.
So if we leave it as is, it'll probably cure. But we're not going to say it's
sure. That makes sense.
It's absolutely final. And the reason I say that is really based on history. Every other standard that every other version of PCI Express that we've had, that we released at 0.7, we went back and made a significant change on.
Okay.
Gen 3, for example, we had an equalization scheme that we defined that we thought would handle every case necessary. And it was just a simple analog filter that we were applying to do the equalization. Turned out that didn't work in the worst cases. So we had to go back and we had to add a nonlinear equalizer to supplement that after the fact. So
Sounds like a
fortunately,
bunch of fun.
the concrete was still pretty wet, and we just kind of pulled it out and did that. And
now, if I understand right from my days in logic, PCIe Gen 4 is kind of a different beast for people who are trying to implement, and maybe.
Well, what makes it different, I think, would be maybe another way to put it. It looks a lot like PCI Express 3.0 from a protocol standpoint. And an encoding standpoint, a lot of components about PCI Express Gen 4 share a lot in common with Gen 3. In fact, you could argue that PCI Express Gen 4 has more in common with Gen 3 than Gen 3 did with Gen 2.
Okay.
So, I mean, Gen 3 was a radical departure from Gen 2, but Gen 3 pretty much keeps a lot of things in place, at least on the surface. The thing that makes Gen 4, I think, a challenge for the industry is that the channels that we have to support are not changing. I mean, if you look in a desktop computer, your average channel length is going to be about 10 inches, 25 centimeters. If you look in today's modern server, it's about 20 inches. It's got 2 connectors. Usually they'll have risers in there for moving things out. That architecture isn't changing. It really can't, because there's a lot of demands being put on the performance of the part, right? But when you increase the speed of the device, then you're automatically having to put higher frequencies through the same channel that you had before.
Okay.
And so you have this thing called insertion loss, which is a frequency-dependent loss, or loss that increases with the higher and higher frequencies. And so if you're doubling the frequency, then you're going to see a significant bump in the increase of loss. And with the increase of loss, your ability to take a signal, drive it into a channel, and see it, and be able to recover it at the end of the channel becomes significantly marginalized. Gen 3, for example, I'll give you a couple of numbers. So Gen 3, in the worst case scenario, after equalization, had an eye height of 25 millivolts. Now think about that, 25 millivolts. That's not a whole lot. Now, fortunately, it worked pretty well. I mean, receivers technology has gotten to be really, really good. But for Gen 4, we're increasing the data rate, doubling it from 8 to 16, and the eye height's dropping from 25 millivolts to 15 millivolts through equalization. It doesn't look a whole lot different than noise at that point.
Yeah.
And that's at the end of the channel. But even then, we can't get to the same 50 centimeter channel and 2 connectors with that signal. So effectively, without some type of significant improvement in the channel or adding some type of repeater technology, we can't do the kinds of channels that we did previously. So for Gen 4, we had to create a new component or define a new component in the specification. Now this had been an optional capability after we released Gen 3. We started to talk about it, but we really made this a much more refined concept and included that as part of the basic specification, and that's called a retimer. So a retimer's job is effectively to take data and pass it through as quickly as possible to allow you to extend the channel length. To meet the requirements. But it, of course, takes more power and it takes more cost. So if you go around the room and you say, how many people were really excited about being able to use retimers? You won't see a whole lot of hands go up, because they're like, And so that's one thing you can do. So the other thing you can do isn't much better, which is you have to go to a lower loss material. Now, everybody uses a thing called FR4. Do you know what FR4 stands for?
I do not.
Do you know what FR4 stands for? Up until recently, I didn't know what FR4 stands for. No, it stands for Fire Retardant 4.
Huh. That was my second guess.
Second guess, right? What's the main benefit of FR4?
If you're going too fast, it won't light on fire.
Well, there is a...
No, when it lights on fire, it puts the fire out. It's a retardant, not a...
Yeah, I heard a long time ago that the reason why electronics fail is because of why the magic smoke comes out.
Exactly. Yeah.
When the magic smoke leaves, it doesn't work anymore. So anyway, FR4 is cheap, and that's why it's used.
That's a good reason.
And, so pervasively in industry. So you can go to a higher, lower loss material, but there's a significant cost, so the cost can bump up significantly. You can double the cost of your motherboard, for example, just in the material by going to a lower loss type of material for the interconnects on the printed circuit board material.
So what type of material are we talking? Like metal conductor, or is it a semiconductor blend? Like they're doping silicon somehow, or how is this FR4? What?
Well, FR4 is fiberglass in a weave. Right, so they have like a fiber mesh that goes through it, and it's done in a press. So it's really like a glue plus fiberglass and a mesh, and you have different layers depending on how many layers of fiberglass or how many layers of conductors that you're running through, how many ground layers you have in the board.
Okay, and this is in your board basically.
Right, and and just because of the nature of the capacitive, the capacitance of the materials that are used, you can have variations in insertion loss profiles and frequency dependent characteristics of the boards, and also impacted by the the types of traces that you run, and so you get into all these signal integrity issues, and that's the point, right? So if you're successful with PCI Express 3.0 and you're thinking, oh well, you smart guys in the PCI-SIG, you're going to have it all figured out by the time I come up, and I'll just be able to do a couple rules of thumb, take all this knowledge I have with Gen 3, which wasn't as hard as you said it was going to be, and so Gen 4 isn't going to be nearly as hard, right?
Sure.
Well, with the eye heights that we're getting to, and the fact that we've got these added complexity of the retimers to get additional length, even though a lot of it is the same in terms of protocol, signaling characteristics, transmitter characteristics, the signal integrity requirements for Gen 4 are probably an order of magnitude greater than what you had with Gen 3, and Gen 3 was no slouch. So this is where you really have to pay a lot of close attention to the details. So you always hear the devil's in the details, the devil's in the details. Just give me a couple of rules of thumb, I'll be good. For Gen 4, that's not going to be the case. It's really going to be understanding not what the one thing is that you are going to be able to do differently that will get you to 16 gigabits per second. It's how you're going to have to make small changes to a number of different things. There's not a single silver bullet that'll get you there. It's not going to be just adding a retimer and I'm there. There's a whole bunch of characteristics from how you lay out the anti-pads, for where you mount the connectors, for adhering to the guidelines that we do provide, to understanding and proving that your channels meet the channel requirements for the specification through statistical simulation. And you really have to pay attention to all the fine-grained details to make sure you're going to have enough margin so that when you go through and build, 100,000 boards, that all of those boards are going to be well within spec.
Awesome.
It's amazing to think we've created technology that can switch a voltage 16 billion times a second. It really is quite amazing. So congratulations on all the hard work.
So you can play video games.
I'm a little, yeah. Thank goodness.
So I can play Minecraft.
And they look more realistic. or you could just go out skiing in Colorado.
Yeah.
Best video game ever.
Best video game ever is a real one.
Just picture the old, what was it, Windows 90, not 92, but the
98.
skier with the Yeti. And
That's why. That was like my favorite game as a kid. Ski Free.
Ski Free. I think it's still around somewhere.
Yeah.
Anyway, as we digress, we're actually out of time for today. Rick, thank you so much for being on. Traditionally, we do a, I'm losing the word. What's the section that we do? Predictions. That's the word. So, Mike, why don't you go ahead and start? What's your prediction for this episode?
Okay. Well, we kind of see it already. I believe one phone manufacturer has done this already, but with PCI Express being adopted in more mobile applications, I think we're going to, sometime in the near future, see more modular style mobile cell phones where you can plug and play different pieces of equipment into it.
I'm really excited about that possibility. Rick, do you have a prediction for us?
I think you're going to start to see the high-speed PCI Express bus appear in places that you wouldn't necessarily have imagined. Like, we're already starting to see a bit of it where the off-the-shelf component mandates that some of the military companies and aerospace companies are involved in. Because like you see autonomous driving kind of starting to come with us, you'll see, I think, the same kinds of enhancements to user interfaces and things like that, and there will be a push to use off-the-shelf components in military and aerospace applications. And so PCI Express will see a larger and larger share above and beyond proprietary buses there. And I think for places, things like autonomous vehicles, which will be a big push, companies like Ford Motor Company and others are actually going to transition to become more technology driven, and where you would think they're very mechanical engineering oriented. I think you'll see a lot of companies go from a traditional orientation, whatever was the basis for their business, into a more technology oriented orientation where PCI Express all of a sudden becomes more important. And for us, we're going to get calls from people that we wouldn't typically talk to or think we would talk to, saying, "Hey, I'm building a new smart toaster that's an IoT device, and I'm putting an interesting display on it, and I want to use PCIe to get the data between, the processor piece and the bus and the overall data bus, into the processor that uses it for display and be able to go back and forth." So
Smart toast. I like
smart toast. Yeah, you'll see it.
I think if you do it right, it could be a dumb toaster, and you could just use your motherboard and hold the bread up to it.
Not if you have FR4, dude. It'd be fine.
My prediction is pretty simple. I think we're going to see a lot more ports on PCs for like externally connecting PCIe type things. So we do it for some of our equipment because we can transfer a bunch of data at once. I'm trying to use words I can use. Transfer a lot of data pretty fast over the PCIe cable. I think that's going to be more and more common, especially with videography and photography, and as that becomes more and more of a thing. So that's all we have time for today on Double E's Talk Tech. Thank you so much for tuning in. If you are designing PCIe Gen 4 and doing other PCIe implementation in your designs, go to keysight.com/find/PCIe, and there are a ton of different app notes and resources out there. Some of them are written by Rick Eads. I think there's maybe some videos out there. If not, this one will probably make it there. So we'll see. But if you're designing PCIe, go check out. The link is in the description, and we will update the description of this video as time goes on with more and more relevant PCIe information.
Great.
So that's all we have time for. Rick Eads, thank you so much for being on the show.
Oh, my pleasure. Thanks for having me here to share some ideas on PCIe.
Yeah, it's been a pleasure to have you. Mike, welcome back. I know we missed you last time.
Missed you too, bud. Thank you.
And I'm Daniel Bogdanoff, and we will see you the second and fourth Thursdays of each month for another episode of Double E's Talk Tech. Thanks for tuning in. Make sure you subscribe to the Keysight Oscilloscopes YouTube channel, by the way. And we'll see you later. Well, that might make it as bonus content. We'll see.
I met Colin Kaepernick on an airplane once, but they probably won't make it because controversy. We don't want people talking about Colin Kaepernick in the comments.
I saw that on Facebook. You were pretty excited.
I was pretty excited.
Yeah. If this gets aired, don't talk about Colin Kaepernick in the comments. Because that'll definitely work.
Welcome to the internet, Daniel.
We should be done.